Good afternoon, everybody. So we're going to talk about SPDY and HTTP 2.0 and how those two relate. It's a subject that's near and dear to my heart. So without making you wait, right, I'm sure everybody has had a long day. This is what we're trying to get to with HTTP 2.0. This is the promised land. So specifically, the first item on the agenda for HTTP 2.0 is we want to improve performance, which is to say latency. And we will actually talk about latency and why that's very important as a focus area for HTTP 2.0. Then specifically, we're going to try and solve this problem called head of line. So if that doesn't mean anything to you, hopefully after this, you'll actually understand what we're trying to solve there. Multiple connections, this is something that we have to do today to make our web apps perform well. Hopefully we won't have to do that anymore once we have HTTP 2.0. And last but not least, 2.0 sounds like a big thing. It's like, what are you guys going to do? Break the internet, change everything? Not quite. The intent is to be backwards compatible with 1.1. Don't worry, your app will run on HTTP 2.0. So with that in mind, I actually want to go kind of deeper and understand why we're trying to make these changes, right? So I can easily just give you, like, here are the things that you will get once HTTP 2.0 is here. But the real question, I think, and the real interesting question is, why do we need it in the first place? And why are we doing this to begin with? So first of all, since we're talking about performance and latency, here are some just like kind of like usability 101 numbers. So there has been a number of user studies done over time. These results are actually old. They're from Jacob Nielsen, but they've held constant. And basically, what this tells you is that when an interaction happens on a page, in your app, wherever, within 100 milliseconds, we mostly perceive it as instant. It's instant feedback, right? You click on a button, you get response. Great. That's what you want. 100 to 300 people start to respond, start to perceive some sort of a sluggish performance, like the button is sticky, and it really depends on what you're trying to do. And anytime you kind of go over 1 second, that's when the user has already made a context switch, right? You're typing something, you press submit, and all of a sudden you're waiting, and now you're like, oh, I need to email Bob, right? And then you lost the user. So that's what we're trying to solve, right? So ideally, we should be within, let's say, 300 milliseconds. And this is why for a lot of sites like Google, Yahoo, Facebook, there's this kind of unofficial 250 millisecond time that all of the sites try to perform within or return a web page within, because we know that if we do that, then it feels fast and responsive. So with that in mind, how are we doing today? We did this study with Google Analytics. So this is data sampled across hundreds of millions of users with real performance data off their phones and desktop computers all over the web. And it turns out this is data as of April 2012, so 5-6 months ago. The median loading time on the web is about 2.7 seconds, and the mean is 6.9. So it's actually pretty high. And mobile is much worse. So roughly speaking, 5 and 10 seconds. And that, even those numbers are incredibly optimistic, because this is based on the latest Android phones, right? So if you're on the latest Android phone, chances are you're also on a fast network because you're the early adopter. So in reality, these are very, very optimistic, and we have a long way to go to get from 10 seconds or 5 seconds to 250 milliseconds, right? There's like 25x in there. So why is that, right? Why do these pages take so long to render? And if you look at data from httparchive.org, which tracks performance data of how pages load across hundreds of thousands of pages, you'll find that an average page on the web today takes about 84 requests to compose, which is to say there are many resources for which we need to make various requests. In the process, we connect to up to 30 different hosts on average, so 30 computers, distinct computers on the network. And all of that combined comes out to be roughly 1 megabyte in size. So an average page on the web today is 1 meg in size and takes 84 requests, right? And we want this to render in 250 milliseconds or 500 milliseconds. That's almost a miracle, but we make it work. And some interesting observations in here, 600 kilobytes out of that 1 meg is images. So if nothing else, optimizing images on your site may be a very good place to look for easy wins for how to accelerate your site. And that's true in general on the web. We find that picking a good image format is very important. So at this point, you should be saying, like, hey, this is cool, the pages are growing in size, but we're also getting much faster networks, right? You listen to any ad on TV, radio, whatever, and there's like 4G LTE speeds and 40 meg uplink on your Comcast, whatever, right? It's like, great, I'll just get a faster connection and everything will be good. Turns out that's not the case. First of all, let's rewind a little bit. Akamai has this site called akamai.io where they report average connection speeds and a whole bunch of other interesting data about general performance of the web. So I just pulled this number for Q1 2012, and this is specifically for the United States. And you can see that within the US, an average consumer is basically on a 6.7 megabit pipe, right? So there's that's the average available bandwidth in the US. And why is that interesting? Well, sorry, we'll come back to that in a second. Hold that thought. That was bandwidth. The other component, of course, when you talk about web performance is latency. So bandwidth and latency, these are the two major things. And here's some data from the FCC report called Measuring Broadband America. So what they're doing is they're deploying nodes within all the major networks to measure the latency between your computer and the network itself, right? So your provider. So this is just the latency between you and the core network, not even to the destination site. And they're finding that on average, if you have fiber at home, it's 18 milliseconds. For cables, 26 milliseconds, DSL, 43 milliseconds. So this kind of gives you a feel for what are you getting in terms of broadband performance. And we'll see why latency is, in fact, one of the crucial metrics for us moving forward. Now, at Google, we also measure this and we monitor this data quite closely. And we know that worldwide, the RTT, so the latency to the Google servers, is about 100 milliseconds on average. And within US, it's 50 to 60 milliseconds. Now, this is data from 2012. The same measurement from a couple of years back also had worldwide at 100, but had US at 60 to 70. So, we've made some progress. We've won back about 10 milliseconds, which is very good news. But nonetheless, that's not enough. And the problem here is that bandwidth doesn't actually help us as much as you would think when it comes to rendering web pages. And the question you should be asking yourself at this point is why? Why wouldn't bandwidth make all of our pages faster? And here's a study that we did. This is from a couple of years back. So this is what kicked off the SPDY work at Google a few years back. And the study was very simple. We took a sample of websites, of popular websites, and we varied the available bandwidth to the user and the latency to the server, right? So it's kind of two independent variables. And you can see the difference in how the PLT, which is the page load time, right? This total amount of time that the page takes to load was affected. So on the left, you have the latency per bandwidth, which is to say we're varying bandwidth. And when you're on a 1 megabit connection, on average, these pages took 3 seconds to load, okay? We doubled the bandwidth to 2 megabits, and all of a sudden the page load time drops almost by a factor of 2. That's a great win. That's what you would expect. But shortly after that, you see this kind of very quick decay. So after about 5 megabits per second, you're getting single percentage wins in terms of page loading time. Which is not very promising, to be honest, right? And why does this matter? Well, think back to the number that we saw earlier from Akamai. On average, a consumer in the US already has over 5 megabits per second. So upgrading your connection today probably won't make the pages load any faster. That's a depressing thought. Now, let's try the same experiment, but by varying the RTT to the server. So this is the latency between you and the server that you're trying to communicate with. And the most obvious thing that you can see is as we decrease the latency, the performance improves linearly. So there's a direct correlation there. And at this point, if you're familiar with kind of the inner workings of TCP, you're saying, well, of course, that's what you would expect. And I'm not going to talk about mobile specifically in this talk, but everything that we are covering here applies directly to mobile, except that the situation there is much, much worse, right? Like orders of magnitude worse. So this is a snippet I took from the Sprint FAQ, right? And they're telling you that on the 4G network, you should expect average latency of 150 milliseconds, right? So if you're one of these early adopters who went out and got the new 4G, that's what you're going to get. If you're on the 3G network, you're going to expect latency of 400 milliseconds. Right? This is pretty brutal. Think back to the fiber at home with 18 milliseconds. You're getting 10x difference basically on your mobile phone, or worse. So in our test, we didn't even simulate the performance going over 240. So we should revisit that test. And the thing to mention about bandwidth and latency is that improving bandwidth is relatively easy, and I put a lot of stars there because I'm sure somebody in the crowd will be like, "What are you talking about? This is incredibly expensive," and it is, right? But it turns out that bandwidth can be increased by just providing more fiber, and fiber is expensive to just lay. But for example, between 2007 and 2011, over 60% of the capacity that was added to our existing infrastructure was through upgrades of existing cables, which is to say we deployed better infrastructure on both ends, better modulation and all the rest, and we got better throughput through existing cables. So there's a lot of wins that are happening there. And there's also the possibility that we could just lay another cable, right? Like if the links are saturated between New York and London, we can just lay another link. It's expensive, but we can do that. With latency, the story is much, much harder. We have this thing called the speed of light. It's rather annoying. A couple of years back, there was that announcement that we figured out how to deliver stuff faster than the speed of light. Turns out it was a broken cable. Damn it. Or a faulty cable. So still fingers crossed. Maybe we'll figure it out one day. But in the meantime, the only thing you can do is to lay a shorter cable, right? So if you have a cable from London to New York that takes 5,000 miles, maybe you can lay one that's 4,500 miles, and that's actually a win. So as an example, just last year there was a project, last year there was a project kicked off by a couple of companies, which is called Hibernia Express. And the entire premise of this project is that they are laying the shortest cable between North America and London, right? And this cable will save 5 milliseconds of latency. And this cable is only going to be used by the financial institutions because they figured out that these guys are willing to pay for this. The project is going to cost $400 million, so that, doing basic math tells you that a millisecond is worth about 80 million bucks. And that's not even the most expensive project. So this gives you a feel, right? Like we're up against some really tough boundaries here. And not only that, but when it comes to latency, we're already within a small constant factor of the maximum of the speed of light. So we can't expect a 2x or a 10x improvement anytime soon unless we actually figure out how to go faster than the speed of light, which is a minor complication. So once again, why is latency the problem, right? We're trying to render web pages. So if you guys are familiar with HTTP, right, there's HTTP 1.1 introduced this concept of pipelining. So the basic operation of HTTP is to say we have one connection and you send the request, you wait for the response. Once we get the response, you can send another request. Very simple model. Pipelining, which was introduced in HTTP 1.1, basically says, hey, you can send me multiple requests, one after the other, but I will only respond in order. So if you send me requests for images A, B, and C, I will send you the entire response A, then I will send you the entire response B, and then C, right? So there's no interleaving between these images or any of these resources that you're requesting. So why is this a problem? Well, in that second diagram, it's very pretty because everything just goes a lot faster. In reality, what happens is that we have this problem called head-of-line blocking, where some requests, so for example, that first request could be a dynamic image or a server action that takes a while, and then everything is blocked behind it. And this turns out to be a huge scheduling problem. So because of this, pipelining hasn't actually seen lots of adoption. It is being used on mobile browsers today, but it's nonetheless, it's hit and miss, right? Because if you schedule something wrong, and you can only guess how you should schedule your resources, you may run into a case where you pipeline these second and third resource, and you would have been better off to wait and send those requests in another connection. So generally speaking, this is an unsolvable problem, right? Like you can guess, but you'll never win entirely. So what is our solution? Has been? Well, we just open multiple connections, right? Like to hell with it. We'll just, instead of sending 6 requests over the same connection, we'll open 6 connections and send a request on each. And this is basically the default number on all the browsers today. This number has varied over time based on what browser you're using, but today most desktop and mobile browsers have this limit of 6 connections per host name. And of course, what do? 6 connections may not be enough because you have 30 images on the page. We do domain sharding, right? So we'll put different subdomains, and then you'll open 30 connections, all right? It's like problem solved. Beautiful. So why is this a problem? Let's go a level deeper, right? We're looking at HTTP. The problem here is that new connections also impose their own penalty. And TCP has this feature called slow start. It's not a bug, it is a feature where the observation that the TCP guys made way back in the mid-50s that we have, the server and the client may have asymmetric links, right? A server may have a very fast connection, the client may not have a very fast connection, and we need to figure out the available capacity between these two channels, or maybe somewhere in between there's a congested link. So to be fair to everybody on the network, we are going to start slow, which is to say we're going to start by sending a couple of packets, and then once you ACK those packets, we will grow this window size. And then you ACK it again, and it will grow again. This is exactly what is happening here, right? We start with 3 packets, we get those ACKs, we increase the window size to 6, so on and so forth. So you can see that it's growing very fast. And if you zoom out a little bit, you will usually see this sort of chart for your TCP performance. This is a new connection being started. It ramps very quickly, relatively speaking, and then at a certain point, a packet loss occurs, and then we enter a new congestion control mechanism, which we're not going to talk about. But this has important implications on TCP performance. This right here is limited on latency. So let's take a look. This tells us that within 3 RTTs, we can deliver 12 segments. A segment is basically 1,500 bytes on the network. So we can deliver 14 kilobytes within 3 RTTs. This is why latency matters. Think back to our original problem. We have a page that is roughly 1 megabyte in size, 80 requests. If you do the math, it works out to be on average about 14 kilobytes. So although we have a lot of requests, they're usually very small requests. Because we're opening new connections, we're always going through this slow start phase, and even though you have, let's say, a 5 megabit connection, we're not able to make use of it because we need to go through this process every single time. So we start by sending you like a couple of kilobytes, and then we wait again, and the entire performance profile of that page is then dictated by the latency between the server and the client, right? That's why decreasing that latency was very important. And that's why mobile is such a hard thing to get right, because not only are the latencies higher, they're also extremely variable due to any number of reasons, right? A car pulls in front of you, the signal bounces, and all of a sudden, weird stuff happens on the network. So one solution that is currently being deployed is called, it's increasing the original window size. So if I go back here, right, we started with these 3 segments. This was the default since about 2002. As of 2010, the new Linux kernels have bumped this to 10 segments. And this is actually a very important win, because with 10 segments, we can deliver most of the resources within that first push before we wait for the RTT. So if you run your servers, you may want to check your kernel and make sure that you have this enabled, because this will actually make pages go a lot faster for you and your users. So, and this is the actual paper from Google that kind of motivated this update. So, that was kind of a detour deep into the TCP stack. So let's talk about HTTP and SPDY. So how do these two relate? I mentioned that we at Google started working on SPDY a couple of years back, and we've actually had very good adoption. So majority of the traffic at Google is now running on SPDY, which is really awesome. And we also had a lot of adoption from third-party vendors, as you will see, in third-party sites. So because of this, the HTTP Biz working group actually kicked off an effort early this year for HTTP 2.0. And this is already in progress. If you look at the rough timeline here, we had the call for proposal that was earlier in the year. This month, we need to draft the first official proposal for HTTP 2.0. So this is like super exciting stuff for those of you who care about working groups and RFCs. But the timeline for the protocol itself is about 2014. So the first note is that SPDY is being adopted as a starting point for HTTP 2.0. That is not to say that HTTP 2.0 is SPDY, right? We're basically saying, look, we've deployed this. It's been running for 2 years. We've learned a lot of things. We can use this as a starting point. It may change entirely, or it may be very similar by the time HTTP 2.0 is here. But the fundamental problems that we're trying to solve are the same. So this is directly from the working group mandate, if you will. We're not going to go through, it's a lot of text. Basically, I grouped them into 3 things. Make things better, build on HTTP 1.1, and be extensible. One of the core features of HTTP 1.1 is that it is extensible. So we want to make sure that we preserve that. We want to make sure that HTTP 1.1 continues to work. And as we covered in the beginning, we want to make sure that we actually address the fundamental limitations of HTTP 1.1. So we touched on this briefly, but here are some examples of the kinds of things that all of us today need to do to work around these limitations. For example, spriting images. Why do we need to sprite images? Well, connections are expensive, right? So what do? We pull all the images together, and then we have this giant CSS hack to position it on the page in the right place. It's quite frankly, it's annoying to do. We know how to do it, but we shouldn't have to, right, if we didn't have this limitation. Domain sharding is a great example, right? We're working around the fact that we have this connection limit in the browser. Resource inlining is the same thing. So all of these things will hopefully get addressed in the sense that once HTTP 2.0 is here, we actually won't have to do this stuff. So life will get easier, which is nice. So HTTP 2.0 will take a while, as you saw, 2014. These things do take some time. So what can you do in the meantime? Well, you can use SPDY. So SPDY is already here. It is supported by Chrome, Opera, and Firefox. And it is compliant with HTTP, as in it's not like an entirely new protocol. HTTP 2.0, this is another quote from Mark Nottingham, who leads the HTTP working group. What we're doing in HTTP 2.0 is we're changing how the data is laid out on the wire. We're not changing any of the semantics of HTTP. So all of the headers that cookies, all that kind of stuff is all there. It's all the same. It's just how it's shipped on the wire. So here is a very quick introduction to SPDY. We're not going to go very deep on this. And this is specifically for SPDY version 2. So SPDY has gone through, we're actually right now working on SPDY version 4. SPDY version 2 is what is being adopted as a starting point for the spec. So this is specifically for SPDY version 2. So first of all, the primary goal of SPDY is to allow you to use one connection and get all of your resources over it. That means we can really open that window very wide, make optimal use of your bandwidth, and everything should just run better. Requests are mapped to streams in SPDY speak. So if you just kind of replace that word, one connection, you have multiple streams over it, and each stream corresponds to a request. And streams can be multiplexed, which is to say they can be interleaved. So I can send you a little bit of data for this image, and then I can send you a little bit of data for the CSS file, JavaScript, what have you, right? So everything's good. It is binary framed, and there are 2 types of frames. There's a control frame and a data frame. And I can tell you that having written an HTTP parser and a server and a client, and having written an SPDY client, the SPDY client took me a weekend. The HTTP stuff took me like a year to get right. So it's a lot easier to work with once you have a well-defined format. So here's an example, right? This is a sample SPDY frame. This is a frame that opens a new connection, or sorry, not a new connection, a new stream. So what we're saying is the first bit says it's a control packet, right? So there's just one. And then we're saying I'm speaking to you in SPDY version 2. The 1 represents that it's a SYN stream, which is to say we're opening a new stream. So this represents the type of packet. I'm going to skip the flags in length. But then you have the request ID. So the client assigns, or every request gets its own ID, such that when data comes in, we can actually look at the frame and say, oh, hey, this is data for request, or sorry, stream number 45, which corresponds to this image. Nice and simple. And then we have priority as well. So you can actually say, hey, I've sent you requests for these 5 images, but now I've stumbled into this JavaScript file, which is very important for me to render this page quickly. Give me a higher priority for this one, right? Push back sending the image data, which is actually a very, very nice feature. Today, browsers are actually sometimes pessimistic. They will find the resources and they will wait, and they will say, hey, maybe there's a JavaScript file coming later, which is actually more important, so I don't want to block the pipes, if you will. So I will wait and then kind of race it, which is like, once again, it's a game you can't win. We're guessing. So this will help us solve this issue. And everything is length prefixed, which is to say, if you ever built a parser, this makes life very, very easy, right? Because the first thing we tell you is like, this is the number of bytes you should expect. If you don't care about this frame, just skip right over it. This is not the case with HTTP, where you need to parse all of the damn headers and the body, and then you like, okay, this is the new request. So this will actually make it much easier. And then we have things like, sending actual headers. So as part of the send stream, the next thing that comes is we tell you, hey, I'm going to send you 10 headers, right? So we encode that directly, and then we say, by the way, here's the length of the name of the header, here's the header, here's the length of the value, here's the value. So it makes, once again, very easy to parse. So this is my terrible artistic rendition of how SPDY works. Bear with me. So we have 3 requests that we send from the client to the server. So these are streams that we open. And then the server says, hey, okay, that's cool. This third request that you sent me, I already have some data for it, so I'm going to start sending you these frames back. And then sometime later, I have data for another, from another request, so I can interleave this stuff. I can send it in parallel, etc. So one connection, everything flows over it, as long as it's on the same domain, obviously. And we'll come back to the, well, actually, it's right here. So domain sharding is a problem, right? So if you've sharded, explicitly sharded your site to have multiple domains, now we need the great unsharding once we go to HTTP 2.0. We need to convince all of you that that is actually counterproductive, and if you put all the resources on the same page, it'll make your life better and pages load faster. So we're still working through how to actually do that well, as opposed to just telling everybody to undo it. So there's a lot of wins that you get out of this performance. There's also some gotchas, especially in situations where you have really high latency networks. We'll touch on that a little bit near the end. So another optimization that is important and that is coming, that is definitely in SPDY, we'll see how it plays out in HTTP 2.0, is we need better header compression. So we know that on average, request response headers, those are sent in plain text in HTTP today. You can compress the bodies via whatever mechanism you wish, but the headers are in plain text. And on average, that's 800 bytes on the wire, right? So as an example here, this is very typical use case today. I'm sending this like JSON payload that says message oh hi to a random server, right? And here's all of the HTTP headers that get appended to those like, what is it? 16 bytes of data that I'm trying to send, right? So the actual payload is like tiny compared to all of this overhead. And that's what we want to solve in HTTP 2.0. So in SPDY, we actually just compress all of the headers, which gives us an enormous win in terms of overall performance. In SPDY version 4, we're actually reworking or trying to rethink how all of that is done. Instead of using gzip compression, we're actually doing kind of our own compressor, which is easier for proxies and others to adopt. So we talked about gzip. Oh, and also in SPDY version 4, we have this idea that we're experimenting with, which is to say, a lot of headers that you send today are the same. For example, your user agent probably doesn't change on every request. I hope it doesn't. Mine doesn't. So why do we keep sending it, right? Wouldn't it make sense when you open a new connection to send that header once and say, hey, this is a connection level header, and if you care, just apply it to every subsequent request, such that I don't need to send it to you. That in itself is a form of compression, of course. So we're also playing with that idea and trying to figure out how we can make sense of this. This may enable very kind of compact representation of headers. So now we're getting into the fun territory. Some people really misunderstand server push. So SPDY does have this feature where we have this observation basically where the server is serving you a file, and the server may know already the other files that you will be requesting, right? Like I'm giving you the HTML. I know you're going to ask for the header image. So why don't I just push the image to you? And that's effectively what server push is. Now, this kind of raises a lot of alarms for a lot of people, rightfully so, because they're saying, well, if you're going to start pushing resources, that may be a problem, because what if I don't want it, right? I'm on a mobile connection. Maybe I have it in my cache. I don't want for you to just kind of use up my data. All you need is like one bad guy to just push me like a gigabyte of whatever's, right? And everything's terrible. So the answer to that is you can cancel it. The client will send a send stream packet that you saw earlier, and you can look at that and say, hey, no, I don't want this. You can decline that. But also, you are already using server push. That is what we call inlining today, right? When you inline, when you use a data URI in your page, you're basically saying, I know you will ask me for this image or whatever, so here it is, right in the HTML file. That is server push, like that's manual server push, if you will. But that's effectively the use case that we're trying to solve. And with proper server push, it actually works out much better because when you inline something into the page, it becomes part of that page. If you have, for example, a small icon that you keep inlining on every page, it will literally become part of every page, as opposed to being in the cache and you can reuse the cache for all the requests. So there's a lot of interesting things that you can do with server push, but there's also some gotchas. And the really interesting use cases for this kind of stuff that I haven't really seen a lot of people play with, but I think it will come, is something like Amazon Silk. So if you're using the Kindle Fire tablet, you are using a speedy proxy. The way it works is when you browse to HTTP sites, the tablet itself has one connection to an EC2 server, or the Amazon Silk server, and that talks over speedy. And then Amazon fetches all of the resources, optimizes them, it may rewrite the images and push them to your tablet, which in theory could accelerate the browsing experience, right, which is great. And in theory, when you're shuttling all of your resources through this proxy, it could keep a very good picture of what's in your cache. So it could be very smart about the things that it can push into your cache. So I think stuff like this will come, and it'll be really, really interesting. Now, the other thing that you need to be aware of for Speedy, and this is up and open for debate with HTTP 2.0 right now, is Speedy does run over SSL. And there are many discussions as to why that is. There are people for philosophical or political reasons believe that everything should be over SSL. And frankly, it is kind of crazy that you can walk into a cafe, start a sniffer, and get a bunch of passwords from a bunch of people that are just browsing the HTTP sites. That's not a good story. I think we're solving that slowly but surely, but that's not the reason why we use TLS for Speedy. Specifically, we use TLS for Speedy because we have a lot of intermediate proxies deployed on the web that operate on all these TCP streams and HTTP streams, and many of them, sometimes for good reasons, sometimes for bad reasons, may drop this traffic. So for example, your antivirus software may actually look at your HTTP traffic as it's flowing and say, hey, you're talking some protocol I have no idea about, smells like malware to me, drop this connection. And all of a sudden, your connection is gone, right? And the client can't communicate with your server. So in practice, even something like WebSockets is deployed, if you're deploying at scale, especially on mobile browsers, you use HTTPS because that gives you an end-to-end encrypted tunnel where these intermediaries can't muck with your data and can't drop the connections. In practice, we find that 80, 90% of the time, everything works just fine, but then 10% of the time, you have no idea. The client just can't reach your server, which is obviously not a story you would want for something like Google.com, right? 10% of our users can't access the site. Not a good deal. So that is the #1 reason for SSL right now. And I mentioned WebSockets, SDHC. Now, for TLS, two things come up whenever you bring up TLS. First of all, speed. If we're talking about performance, and the whole point of Speedy is performance, doesn't TLS work against us? And there are specifically two things, CPU and latency. So for CPU, it is definitely true that, let's say 5, 6, 10 years ago, the handshake, the cryptographic handshake was a bottleneck. You actually needed dedicated hardware to offload that too. But today, all of the modern hardware has all of the stuff built right into the hardware such that it's actually very cheap. So this quote that I have here from Adam Langley, who's our SSL guy at Google, and this is from his blog. When we turned on to SSL Google-wide, our CPU load on all of our servers went up by 1 or 2%. There's no hardware acceleration. This is all done in software. Facebook also runs all of their SSL in software. So the handshake latency, the CPU load is actually not that significant. There are optimizations that need to be made and can be made within the SSL stack for better performance, like adjusting your SSL buffers, but that's really not the issue anymore. And I hope we can put that one to rest. The bigger issue, if anything, is the latency, because TCP, when you establish a new connection, has the handshake, which is a full round trip that before any data can be sent. SSL requires up to 2 additional round trips, which is terrible if you think about it, right? I'm on my mobile phone, I need to establish an SSL connection. Let's say my latency is 400 milliseconds. That's over 1 second before I can even send you the GET request. I mean, that is terrible. So to address that, we have a couple of proposals out there. They're experimental, called false start and fast start, which try to reduce the extra round trips, from 2 down to 1, and there's even a proposal that may actually take it down to 0 by basically remembering kind of state on both ends. So definitely an issue, but it gives us a lot of important characteristics that we saw earlier. And I should also mention that as part of SPDY, so SPDY uses this protocol extension called Next Protocol Negotiation, which pushes the negotiation of what protocol you're going to use into the SSL handshake itself. So there's no extra round trips. If you think about WebSockets, the way that's done is you send an HTTP request with a header that says, I want to upgrade to a WebSocket connection, which then initiates another round of a round trip. We bypass that with TLS NPN. So if you're thinking of deploying SPDY, you will need TLS NPN, and that is in OpenSSL by default nowadays. So who supports SPDY today? Chrome, since ancient times. We have support on Android browsers. We have support on iOS. So this is a screenshot I took of Chrome running on iOS. It does understand SPDY. It uses the same network stack, so you get all the same things, which is really nice. We have Apache modules. There's an nginx module, Jetty, Netty. So a lot of the app servers today already support SPDY, and I'll actually show you some examples of how to get started a little bit later. We also have big sites outside of Google with support for SPDY. So Twitter supports SPDY. We have WordPress. WordPress runs on nginx. They were actually the ones that sponsored the nginx implementation of SPDY, which is really cool. Facebook is not running on SPDY, but they've indicated that they are experimenting with it, which I think is really cool. And there's also a lot of commercial pickup on this stuff as well. So Akamai announced that they will support it Q4 this year, which I guess is now. We have F5 with their SPDY gateway, etc. And of course, I mentioned this already, if you are using Google services, you are, in all likelihood, accessing them over SPDY, which is pretty neat. So I figured I'd answer some questions preemptively, because I know that these questions come up all the time. Do I need to modify my site to work with HTTP 2.0 or SPDY? And the answer is no. We saw that nothing really changes. HTTP headers are the same. We're not asking you to change your angle bracket syntax or anything like that. But you can optimize your sites to make better advantage of SPDY. The biggest one is probably the domain unsharding, if you will. That's the #1 win. And then the others are probably actually on the server. So making sure that because you're using SSL, you have the optimal certificate length. You're not padding extra data in there. And you have your C window set to 10 and other things like that. So it's more in the server than the client. And I think we actually covered the rest. So sounds complicated. Are there drop-in solutions? Yes, we saw, right? There's SPDY. If you have an app on App Engine, you will inherit the stuff for free, which is really nice. But, there's a gotcha. And there's always a gotcha, right? So imagine in 2014, we have HTTP 2.0 and then life is beautiful. Problem solved, right? Well, not quite. We took a problem in HTTP 1.1. We solved it by going to HTTP 2.0, and now we have, as usual with performance, we unlock another bottleneck. And now that bottleneck lives in TCP. And in reality, all we've done is we've moved the head-of-line blocking issue from HTTP into TCP. So why is that? Recall this diagram. So TCP provides this abstraction of a reliable delivery on top of what is effectively an unreliable network. There is packet loss on the internet. In fact, it's on average 1 to 2% packet loss rate. And what that means is we have a resource that we're trying to ship to the client. We push out a whole bunch of packets or segments onto the network. And let's say one of those packets, one of the first ones, gets lost for whatever reason, right? The rest get delivered all just fine, but the first one is lost. What does that mean? Well, that means that the receiver will keep all of the packets that are coming after it in its own buffer and wait for the first one, because it promised you that we'll deliver everything in order. So that lag between losing that packet and then having to retransmit it is what introduces this head-of-line blocking. So arguably, this is not maybe as big as the problem originally in HTTP 1.1, but this introduces a lot of jitter and kind of random delays into the performance. So if you're trying to build a real-time kind of interactive experience, this may actually be a problem. This is the reason why we transfer game state, video, and audio kind of stuff over UDP, right? Because if you lost that packet, that's okay. Maybe I can pave over it and do something else. So that is a problem, and we don't have a good solution for it. This was not a goal for HTTP 2.0 to solve, but we are aware that this is a limitation. And this may be a limitation specifically on these kind of really high latency networks when you have a user from Malaysia talking to your server in, I don't know, here, right, in San Francisco. So that's all cool. What do I need to do to actually take advantage of this? I have a website that's running right now. How do I get on SPDY? And the answer is it's actually pretty simple. So there's, depending on which stack you're running on. For example, Apache, we have a module that is being developed at Google called ModSPDY. It is literally just a filter that you install into your server, and the rest is taken care of. So remember, once again, we're not asking you to modify your pages. We're just making better use of the underlying connection and how the data is multiplexed. So if a client comes with a Chrome or Firefox browser to this Apache server, it'll just deliver it over SPDY. No difference there, which is really quite nice. And to get started, you download the package. In this case, I'm using a Debian package. You enable it in your Apache. You restart Apache, and you're up and running, which is pretty sweet. And also, Apache and other servers are often used as a front-end, a terminating node in front of your app servers. So your app servers could be written in Ruby. It could be even Node. I don't know if somebody would do that, but maybe. There's a really good tutorial in that gist link, and I'll share the slides at the end for where a guy wrote up a sequence of steps for enabling Apache in front of his Erlang web server, right? So he can, whatever technology is on the back end, even if it's a Java app server, you can put Apache in front, you can make use of this. And what will happen is Apache will terminate the SPDY connection, the SSL connection, and it will relay the messages in plain HTTP to your backend. So your backend won't even know that it's talking in SPDY. nginx, as I mentioned, has support. Right now it is experimental. It's a patch, although through the rumor mill, apparently they're merging the support into core very soon, as in like maybe weeks. So today you would actually have to download this patch. It is an official patch from nginx, and you just build it with the latest OpenSSL and you're up and running, which is also quite nice. If you're running a Node server, very simple. There's a great module called Node SPDY. And you can see here that we're just setting up an SSL server. If you've ever written a Node server, this is just your SSL server, except that we're calling spdy.create server. And that's all there is to it, really. And the server takes care of the rest. And Node SPDY actually also supports server push, which is quite nice. So you can do really interesting stuff with it, and you can experiment with it quite well. For Java, I was going to copy the pages of XML and markup, but I figured I shouldn't. So having said that, there's very good implementation for Jetty. The Jetty guys have done an amazing job. So at the bottom, there's a link that will walk you through all the steps. You basically, a couple of things. You have to add an extra jar to your class path, which adds this NPN support for SSL negotiation. That's step number one. And then you use their SPDY client or SPDY server to enable it on your Java app server. There's 50 pages of XML in there somewhere, but it works. And now finally, if you're the client, how do I even know? How do I debug this stuff? So there are, for all the browsers that support it today, there are extensions that you can install just if you're curious. If you're browsing around the web and you're curious, am I on SPDY or am I using HTTP? So Chrome has a SPDY indicator. You can search for it and you'll find, I have no idea how this, it's a little kind of green bolt icon. This is not an official icon. I have no idea where it came from. But I think the first implementation of this plugin was for Chrome. I think the guy just picked it, and now all the browsers adopted it, which is neat. So there you go. So it'll show up as a green bolt in Chrome, green bolt in Firefox, and in Opera it actually has a dedicated space on the right side, which is pretty cool. So these are just kind of indicators for when you're on the site that supports SPDY. In Chrome and also in Firefox, you can also query from the command line and see which version of SPDY am I using. So for example, here I'm just pulling up my console and I'm typing in window.chrome.loadtimes and I get this object back, which says that we negotiated over NPN SPDY version 3. So I'm speaking SPDY version 3, and this page was fetched via SPDY, and it was negotiated over NPN. So there's useful metadata there. But this now tells you that you are on SPDY, but can you go deeper? And the answer is yes, absolutely. And probably one of the best tools is the Chrome Net Internals pane. If you guys have never played with Net Internals, this is an excellent reason to peek inside and see how it works. So we have this separate pane for SPDY that you go into, and you will see all of the open SPDY connections. And I will actually, with luck, I will show you this. Okay, so SPDY.io is just like a silly node server that I'm running that is delivering this hello world message over SPDY, right? So I'm running this, and now I'm going to go to Chrome Net Internals into SPDY, and you can see that SPDY.io is listed as a SPDY version 3. Let me make that a little bit bigger. So we're talking SPDY version 3 to SPDY.io, and I can actually click on this connection. Let me see. There we go. And we have our SPDY session. And then I can click on the SPDY session itself, and you can actually see the exchange. This is the stuff that flows on the wire. So you can actually see the SPDY frames as they're exchanged. So for example, we have this syn stream. Remember we talked about syn stream, which is the, I would like to open a new request to the server. And we're saying, it's okay, so I'm sending a syn stream. Here are all my headers, host method, accept headers, all the rest. So this is what you would expect out of a regular HTTP request. And then we get some 404 data back. So if you need to debug SPDY, this is probably the best tool to do that, so definitely give it a try. So with that, I'm happy to take questions, right? As a quick summary, and there's a mic in there if you guys have any questions. But in the meantime, a couple of things, right? So just to come back full circle, the core goal for HTTP 2.0 is to improve latency. How are we going to do that? We're trying to remove the bottleneck in the existing HTTP 1.1 implementation, which is this head of line blocking. We want to be able to mux multiple requests over the same connection, such that we can open that big and wide and get all the resources as fast as we can. It'll have all the same semantics, and in the meantime, you can use SPDY to accelerate your site. So one common question is, well, what should I expect on my site? And the answer is, it really depends on the architecture of your site. If you serve majority third-party content and you have tons and tons of widgets, you're not going to get as big of a win. But we have seen big improvements. The original goal for SPDY was to accelerate the loading time by 40 to 50%, and we think we're on track for that. Your actual results may vary, but this is very cool because you can enable this. Your admin can enable this on the server, and the site just goes faster. You haven't done anything to the underlying pages. So that's the quick summary. The slides are online, so if you go to bit.ly HTTP2-SPDY, you can find those there. Thank you.